Okay, so in this kind of last set of lectures for the course, we're going to look at what happens when we have a PDE with external terms, which is what most people mean when they say non-homogeneous. So again, I'm just going to go back to our classic example. We're going to look at the following equation. I'm going to use slightly opposite notation than what I have in the notes here, but you'll be able to follow along. So this is the equation. The t derivative of u is equal to the double x derivative of u plus some external force, which we can call q of xt. Now, this is like just some, well, it's an external force. So whatever that happens to be, you know, if this could be like, if this is a heat equation, this could be a blowtorch or whatever, or a piece of ice that you put somewhere in there. Okay, so whatever the external source is. And then again, we're going to look at our Dirichlet boundary conditions. U of 0t equals u of 1t, and they're both equal to 0. And then we're going to look at our initial condition, u of x0 is equal to f of x. Okay, so we want to solve this equation. And again, the important feature here is that we have an external forcing term, or an external source or sink of heat, if this model's like in a heat equation. Or if it's just a generic diffusion equation, let's say we're modeling like the dye in a pipe or something, this would be like you're just dropping dye in as the experiment goes on, something like that. So there's a number of different things that it can model, but mathematically, like I keep using the same problem over and over again, because mathematically, because I want you to get the basic algorithm and idea down for solving these non-homogeneous problems, and then you can extend them to other problems you might actually care about. So what we're going to do, if you think back to your ordinary differential equations class, one of the things that we did, if you think about the method of variation of parameters, how did you apply the method of variation of parameters? Well, you first forgot about the q, found the solution to the corresponding homogeneous equation, and then used that to find a particular solution to the non-homogeneous equation. And we've already done something very similar when we were looking at problems on the entire real line. So what we're going to do is we're going to solve the corresponding homogeneous problem, which is going to be the t derivative of v is equal to the double x derivative of v. V of 0t is equal to v of 1t, and that's equal to 0. And v of x0 is equal to f of x. Okay, so it's just the same problem without the q term. Okay, so now again, we can solve this problem, exactly. We can find the eigenfunctions and eigenvalues exactly, but I just want to do this generically. We know we're going to get a set of eigenvalues, lambda k, and a set of eigenfunctions, phi k. Now, for this problem, the way that I'm going to state it, lambda k is going to be equal to k pi squared, which is typical. That's what we've always had. But phi k of x for this problem, phi k of x is going to be equal to the square root of 2 times sine of k pi x, and that's just so that it's normalized. In other words, so if you do the integral of phi k times phi k, you get 1, and if you do the integral of phi k times phi j, you still get 0. Okay, so we know that that v of xt can be written the following way. It can be written as the sum k equals 1 to infinity times bk e to the minus lambda kt vk of x. Like, we know we can write vk that way. So the point is that we solve this homogeneous equation to get these eigenvalues and eigenvectors. Well, what we're going to do is we're going to apply the idea of eigenfunction expansion, not just to v, which is a solution to this equation, but to u, which is the solution to the equation that we actually care about. So what we know then, and I'm just going to warn you, the notation here gets pretty, there's going to be a lot of like summations, integrations, summations, stuff like that going on. I just want to warn you. So u of xt, for any fixed value of t, we can expand this in the eigenfunctions for the homogeneous problem. So we can write this as the sum k equals 1 to infinity. And I'm going to use ck as my coefficients. I don't want to use ak or bk because we've been using those for homogeneous problems. So we're going to have ck of t pk of x. And now we're going to see what happens if we take this and we plug it into the non-homogeneous equation. So we're going to take this and plug it into the non-homogeneous equation. Well, when we take the t derivative of it, we're going to get the sum k equals 1 to infinity ck prime of t pk of x. That's like the left-hand side. Now the right-hand side, what we're going to get is we're going to get the sum k equals 1 to infinity. And because I don't want to actually write out every single thing, when I do the second derivative, it's just going to hit phi k. It's going to give us phi k double prime. And we know that is equal to minus lambda k, and I'll go ahead and write this ck of t, times phi k of x. So I'm just using the fact that we know that that phi k double prime is equal to minus lambda k phi k. That's what it means for phi k to be an eigenfunction relative to the eigenvalue lambda k. And again, for this particular problem, we know what the explicit formulas are for phi k and lambda k, but for the sake of generality and wanting you to have like a generic version of this in your mind, I'm just going to write it like this. Okay, now what about q of xt? I need to add the q of xt term. So let me just put this as a placeholder now so there's no confusion. Okay, but what I want to do is the following. Q of xt, well, if we assume that q of xt is regular enough, that is, it's differentiable enough, we can also write it as an expansion in the eigenfunctions phi k. And so we can also write this as the sum k equals 1 to infinity. I'm going to call it little qk of t because we're going to get a different coefficient for every k or for every t. Qk of t phi k of x. So qk of t phi k of x. So I'm going to take this, and instead of writing q of xt, I'm just going to write this all together. So we're going to have minus lambda k ck plus qk of t times phi k of x. Okay, now because I need to use this room over here, I'm going to erase this. Now what is qk of t? Well, just using the general theory that we've seen, just based on orthonormality, qk of t is going to be the integral from 0 to 1 of q. Okay, so we're going to be integrating in this variable, in the x variable, but I'm going to use y as the dummy variable. So it's q of yt phi k of y dy. In other words, we're not qk is not what we're solving for. We don't know what the ck and t are. That's what we're solving for here. But we know what qk of t is. It's given by this formula here. Big Q is given, phi k is given now that we've solved the homogeneous problem in principle, and so we know what little qk of t is. Okay, so now what's going to happen is for every we're saying these two things are equal to each other. If U is a solution to the PDE, these two things have to be equal to each other. Well, the only way this can be equal to each other, given the linear independence of the phi k's, the only way these two things can be equal to each other is if the corresponding coefficients are equal to each other. In other words, if ck prime, and these are all functions of t, so this differentiation is with respect to t. So ck prime is equal to minus lambda k ck plus qk. Well, we're in good shape here because this is a first order differential equation. It's not homogeneous, but it's a first order differential equation and we know how to solve it. So if I add lambda k to the other side here and do integrating factors, I'm going to have ck e to the lambda kt prime. Okay, I added ck prime plus lambda k ck. This gives me a first order non-homogeneous differential equation. And for an equation like that, you can use a method of integrating factors. That's one way you can do it. And then integrating factors e to the lambda kt. And then on the right-hand side, since going from here to here, what I've really done is I've multiplied both sides of the equation by e to the lambda kt. Over here, we're going to have qk of t e to the lambda kt. Okay, so what I want to do now is I want to integrate both sides of this equation from I want to solve this. But I want to be a little more careful rather than just looking at antiderivatives. So I'm going to integrate both sides from 0 to t. So these t variables are going to become tau variables. They're going to be the dummy variable. So what this tells me is that, let me just make sure I'm in the correct spot in my notes here. When we do the integration over here, when I integrate this from 0 to t using the fundamental theorem of calculus, it's going to be ck of t e to the lambda kt, ck of t e to the lambda kt minus that evaluated at 0, which is just going to be ck of 0. And this is going to be the integral from tau equals 0 to t of this function right here. An integration variable is going to be tau instead of t. So we're going to get qk of tau e to the lambda k tau d tau. Now we care about what ck of t is. So we're going to solve this for ck of t. So we're going to add ck of 0 to both sides and divide by e to the lambda k, and we're going to get ck of t is equal to ck of 0 times e to the minus lambda k t plus e to the minus lambda kt times the integral from tau equals 0 to t little qk of tau e to the lambda k tau d tau. Okay. So now I'm going to rewrite, so I want to take this expression here, I'm going to leave this, basically erase everything under it, but I'm just going to write out what the formula for ck of t is. Okay, you'll see what I'm going to do. So I'm going to leave this here for now because I'm going to be copying it. So that's ck of t, and so this is going to be equal to the sum k equals 1 to infinity. I'm going to put this first part here, so I've got two different terms. Every ck has two different terms. There's a ck of 0 part and then the other part. So I'm going to break this up into two different terms. So we're going to have ck of 0, e to the minus lambda kt times phi k of x. And then it's going to be plus this other term. So we're going to have plus the sum k equals 1 to infinity. This part right here. So this is e to the minus lambda kt times the integral from tau equals 0 to t little uk of tau e to the lambda k tau d tau, and then we're going to multiply this by the same phi k of x. Okay, so that's what we have there. So now I'm going to erase this part here. Okay, so let's start replacing these things with what we know they're equal to. So ck of 0. So let's think about what ck of 0 is. Well, if you plug in t is equal to 0, we have an integral from tau equals 0 to 0. So this entire sum is equal to 0 when t is equal to 0. That's equal to 1 when t is equal to 0. So in other words, when t is equal to 0, we've got our initial condition, f of x is equal to u of x 0, which is just going to be this sum right here with that term being equal to 1. In other words, it's just like we've seen before. So k equals, so what we're going to have here is the sum, k equals 1 to infinity. Ck of 0 is the integral from 0 to 1. I'm going to use y again as my variable of integration. F of y, Ck of y, dy. So what I just wrote down is a formula for Ck of 0. E to the minus lambda kt Vk of x, and then plus this sum over here, which we're not done dealing with yet. So plus the sum k equals 1 to infinity e to the minus lambda kt, the integral tau equals 0 to t, qk of tau e to the lambda k tau, d tau Vk of x. Okay. So I'm going to rearrange this sum in place. So what I mean is the following. I'm going to move the integral to the outside. So we're going to have the integral here from 0 to 1. This is y going from 0 to 1. And then I'm going to put the f here. So we're going to have f of y. And then the sum, k equals 1 to infinity. So now the f of y is already there. So I'm going to have Vk of y. I wrote tau there instead of t, but I should have written t. So we're going to have e to the minus lambda kt. I had a tau there before, but it should have been a t. E to the minus lambda kt. Vk of x, Vk of y, dy. Okay, we've seen arranging it this way before. Okay, now I want to come down that second term over there. I just want to write out what that is. So what we're going to have is we're going to have the sum. Now what I'm going to write is just the second term here. I'm going to combine it all in a minute, but it's just going to be the second term. So this is equal to the sum k equals 1 to infinity. We're going to have e to the minus lambda kt. We're going to have the integral from tau equals 0 to 1. But now I'm going to put my formula for little qk. So I'm going to put my formula for little qk. But keep in mind I've got qk of tau here, so that t is going to be a tau. So now little qk of tau is the integral y equals 0. Sorry, this is tau equals 0 to t. Isn't it? Y equals 0 to 1 q of y tau Vk of y dy. That's this right here. This integral is little qk of tau. So now I'm going to write e to the lambda k tau d tau Vk of x. Okay, so just look at that in a minute, because I'm about to rearrange this as well. Okay, the first thing that I'm going to do is I want to interchange the role of the, or not the role, but the order of the differentiation and the integration. Okay, I just want to make sure that I get so this is y equals 0 here. So the y integral is going to be the one on the outside. So we're going to have y equals 0, y equals 0 to 1. And again, all of this down here is just the second term. So I'm going to have y equals 0 to 1. Tau equals 0 to t. So my sum is going to go here. So I haven't forgotten the sum yet. I need to put the sum notation back. So e to the minus lambda kt, lambda k tau. I can combine this into one exponential. So I'm going to do a couple of things. I'm going to move the q of y tau over here. So I'm going to have q of y tau, and then I'm going to have my sum, k equals 1 to infinity. Now I'm going to have my exponential. I'm going to combine that into 1. So it's e to the lambda k tau minus t, phi k of y. Then I'm going to have my phi k of x, phi k of y, phi k of x, phi k of y. I'm going to have my inner integral, so d tau, and then my outer integral, dy. Okay, now I want you to observe this. Compare these two functions, this function and this function. What is the difference between this function and this function? The only difference is that instead of, I have a t here, let me actually write this as minus lambda k t minus tau. Okay? The only difference is that instead of I have a t here and a t minus tau here. Other than that, they're the exact same. So that function right there is something called the Green's function. We're going to write it in the following way. And we're going to look more at the Green's function in the following video. So one way that we can sort of think about the Green's function is I can think of it as g, x, y, t, tau is equal to the sum k equals 1 to infinity e to the minus lambda k t minus tau phi k of x, phi k of y. And now what I can do is I'm going to erase everything. You're just going to have to remember what I have written or copy everything down. So I can write this entire thing in the following way. I can write the entire solution in the following way. I can write it as the integral from y equals 0 to 1 f of y times g of x, y, t, 0, dy. This is the part of the solution that corresponds to the initial condition, and then plus the integral y equals 0 to 1, tau equals 0 to t, q of y tau times g of x, y, t, tau, d tau, dy. And this is the part of the solution that is influenced by the external force. Okay, so you did very similar things in your ordinary differential class as well. You wrote the response as a linear combination of the beginning, the initial condition, which is what we have here, plus the response to whatever the external force is, and that's what we have here. It's very similar to how, conceptual is very similar to what you did in your ordinary differential equations class, only here it's a little bit different. Notice also that if we want to know what's happening at time t, it only depends on q before time t. So if I want to know what's happening at time t, it only depends on what is happening, what q has done before time t, which makes sense. This is sort of a causality principle. This is one of the reasons I mentioned a long time ago how we can never really think about, even though Laplace's equation has two variables, an x variable and a y variable, and the string equation has two variables, a t variable and an x variable, it really does not make sense at all to think about Laplace's equation as one of those variables representing time, because the corresponding causality principle doesn't exist. That's just sort of an aside comment. If you didn't, that's not the main point at all, but that's just sort of an aside comment that came to my mind. Now, what's going to happen here, again, the response at time t depends only on the input or the external force or sink or whatever Q is, however, whatever it represents physically, for all times between 0 and t. But of course, it does not depend on Q for time after t. And again, that makes sense, sort of a very reasonable causality principle. Okay, that's it for this video. In the next video, like I said, this is something called Green's function. We're going to look at it again, sort of in an eigenfunction expansion way, and see where things can actually go wrong, because there are some implicit assumptions that we're making here on lambda k that will make this be a little more challenging in the case in those cases. But this could be a short video on that, and then after that video, we're going to look at like explicit ways in which we can compute Green's function.